Hello, today I want to teaching you the lecture 12. It's about Planar's mechanisms. And after we come to this, you will find that the models, they are different, right? At lecture 10, we have studied the two bar, or this bar model. And for lecture 11, we started rolling without slipping models, right? Now we will start a new model. It's about planar mechanisms, slider crank mechanism, geometry approach. We will also include two models or two models for this lecture. One is slider crank mechanism. It looks like this one. And one is the 4-bar linkage example. Okay. And next lecture we will also study 4-bar or 2-bar linkage for rigid body. Okay. Here we have also 3 examples. The first one example. Let's look at the example. For this example, for every example, we will have 2 approaches. The first one approaches is geometry approaches. The second approaches is vector approaches. Let's see the geometry approaches first. It's very simple. The approaches, let's see. Is that the first, you just find out the relationships for their x and y components. Like these questions, the input for us would be theta dot equal omega. The output for us would be sp dot phi and sp dot and phi dot turns of the position piston for one cycle of theta, right? And for the geometric approach, first you should think about the x components, and then you should think about the y components. Like the geometry, it will have 2 components. This one. For this bar, it will have 2 components, this one. So in the y direction, they will equal. And in the x direction, they will equal the sum of them, right? So with theta as the input non-variable, these equations can be easily solved for the output variables, sp and phi. The vector diagram in figure 4.15 shows we can also use the geometry like triangle vector, the sum of them together. With theta as the input non-variable, this equation can be easily solved for the output variable, sp phi. The vector diagram in figure 4.15 shows the position vectors RAB, RBC, and RCA. For these vectors, you can plus them together. But these two are the same. For this method and for this method, the purpose of them, I want to find out the x components and y components relationship for the bar. So for next, we should differentiate it. Because let's go back to the problem. You would like to us to calculate the sp dot, phi dot, and sp dot, phi dot. Actually, we should do the derivative first. Then we can get a relationship which will include the sp dot and phi dot. Phi dot, okay. And let's differentiate it again. We will get sp dot, phi dot, okay, phi dot, yes. And the difficult point, I think here would be the calculation. But as we said before, you should see the phi, the sine phi, like is a composed function. So when you derivative this one, you will equal to phi and phi dot. This is the difficult point. This is the notative point. And next one, you just made them. Because, as you can see, we just use the algebraic knowledge. Like, these two are the unknown we want to choose. These two are the unknown we want to choose. Okay? You rearrange them like this way. Then you can find out that. Okay? So here has a summary. The engineering analysis tasks are accomplished by the following steps. Vary theta over the range of 0 to 2 pi, using discrete values theta i. For each theta I value, solve equation 4.16 to determine corresponding values for phi i. And use equations 4.18 with non-values for theta I and phi I to determine phi I dot. Use equation 4.19. This one is 4.19 to with non-values for theta I, phi I, and phi I dot to determine SPI dot. About SPI versus theta I. Okay, and for SPC as the input with theta and phi, theta dot and phi dot, and theta dot and phi dot as the desired output coordinates. The equations for the vertical. Okay, it's another similar example. Sorry, I do not mention it just now. But let's see the same equations. It also makes the S and Y components. And that's derivative, first derivative, then you can calculate the output you want. But in mechanism, it will be the 2 different mechanics, maybe something like this, okay? And that's vectors approaches for velocity and acceleration approach. Let's see. Actually, this method would be the most general way. So, as you can see, applying the velocity results of equation 4.3 separately for link 1 and 2 gives something like this. Because we can find 2 points. The first point, the second point. The first point, second point. So we can write 2 equations. This one, also it is in the assumption. The formula is the rigid body formula, as we have talked about on lecture 10. Okay, the rigid body. So we use the rigid body formula. And the key point I see is how it removes. So A is fixed, but C is not fixed. Okay, C is not fixed. And for VA and VC, and you will find that they can equal, right? Because you should find the coincide point is B. So with this same point, you can create the equilibrium or the equal functions for all of them, right? And VB will equal to VA plus omega 1 cross product RAB. And it will also equal to VC minus omega 2 cross product RAC, okay? So next one, since point A is fixed on the SY system, VA is equal 0. Yes, similarly, the VP would only have one direction. It would towards this direction, okay? So the velocity of it would this one. And the vector omega 1 is the angular velocity of link 1 with respect to the omega. They could also know. The omega 1, the omega 2, they could be known, right? And the direction of that, I have told before. If the angle is counterclockwise, it will equal positive. But if it is clockwise, it will be negative, okay? The position vector RAB and RBC, you can also define. Like RB, when the point B, it will be R cosine theta, R sine theta, right? And RCB, the B, let me see about it. It could be, yes, maybe it was a little hard for us to have its vector, the position vector. Yes, but you should notice that because the RBC and RAC would be the relative distance between B and C. So it's nothing to consider where you state the local. You can use the local coordinates. Like if I make the local coordinate here. For point B, it will equal 0 and L2 times sine phi, right? And for this one, it will equal L cosine phi and 0. So the distance between them with cosine phi and minus L2 sine phi. There's no problem. Okay, there's no problem. So you should know how to find out the position vector. After that, we get the O parameter. So we can calculate some unknown. Like VA is 0, omega 1 no, RAB no, VB no. VC no, omega 2 no, RBC no. So substituting in here, right? And carrying out the cross product and gathering. After that, you can get the solution for this in S and Y components. Okay, in S and Y components. To find the acceleration relationships, applying the second of equations 4.3 to figure 4.70. Yes, we have finished our velocity results now. The next step for us is to find out the output and input relationship for acceleration using the vector methods. To find the acceleration relationship, applying the second of equations 4.3 to figure 4.70, you can use the same method. Like the coincide point together with AB and BC would be point B. You choose point A and B to make a formula. You choose B and C to make a formula. And then you make them the equal function. With AB, you can find that. AA's the velocity would be also 0. And AC will also only have one direction's acceleration. Omega 1, omega 2 are also easily known. So the angular acceleration of link 2 with respect to XY system substituting gives. You can also make such a function. You could also make such algebraic divide them into X and Y components. Okay, X and Y components. So you will find that actually it's not very difficult. So after introducing it, we will introduce a 4-bar linkage example. The first one is geometry approach. A 4-bar linkage example. Let's considering the following engineering. Actually, we will also have 2 approaches. The first approach is geometry, and the second approach is vector. And also the same for geometry approaches. You should find out the S and Y components. Okay, but like here, the S and Y components. The X and Y components. And figure 4.19 shows a closed loop vector representation that can be formally used to obtain equations 4.21. And the results from figure 4.19b can be stated RAB plus. It is another way for you to have the resultant vector. Okay, but these two understand. You can choose one, but I will always choose this one. Okay, after that, we just restating or rearranging them to make the output is on the left side or right on one side, and to make the input in one side. This is the technique for you to rearranging the formula. The technique or the skill of this one is just make the output like the output on one side, and the input at the another side. That's the technique, that's the key thing, okay? And next one, we will show alpha as the input coordinate and beta and gamma as output coordinate. Differentiating with respect to time is L2 sine beta dot minus L3 sine gamma dot and L1 sine alpha dot. Differentiating them and using the metric to rearrange them more easy to calculate. Why we need to rearrange them? Actually, it's just simple. It just made us to simplify the calculation of us, okay? And the next step, maybe you will be curious about how to solve this metric. We just use the Planar rule. If you are interested in Planar rule, you can see the next lecture. I would provide a lecture to talk about this. Okay. So just now you just need to know you have used the Planar rule to calculate out the variable. And the solution is undefined for beta plus gamma equal pi 0. Differentiating equation gives this one, okay? And differentiating then again, and just using the metric, because or in metric form. In metric form, it will be more easy to calculate it. So let's have a simple like summary. But it is the same. You will find that the engineering analyzing task is accomplished by executing the following sequential steps. First one is vary alpha over the range 0 to 2 pi. We should notice the range area of that. Okay. And the second one is for each alpha I value, solve equation 4.22 to determine corresponding values for beta I and gamma y, and enter equations with known values for alpha I, beta I, and gamma I to determine beta I and yi, and enter equations with known values for alpha I, beta I, and gamma I and beta I, gamma I dot. Okay, to determine beta I and yi dot and plot that. Okay, and plot it. And the following we do not need to see that because it's just simplified processes. We just use like this one to make it across h1. That's okay. That's okay. We do not need to see it very curious. That's okay for the following. But we will also talk about a very important method is vector approach, and it will be most general one, right? Vector approach for velocity and acceleration relationships, starting on the left with link 1 and looking from point A to B gives VB. Okay, the same. You find that the same approach, although there are 3 bars, but you can also find the relation. Like find 1 bar, we can write this equation. For the third bar, we can find this equation. And for the second bar, you can find this equation. And how could you find this? But you should know the meaning of that is that A and D will be unstable. No, it's static. Okay, it's static. So omega 3 you can know. Omega 1, 2, 3 you can get. RAB, RDC you can get. VA, VD you can get. Okay, VB. Let me think about it. Maybe we could just use this one. BC will equal VD plus omega 3 cross product RDC. It will equal VA plus omega 1 cross RAB. Omega 1, but it is these two are 0. So it becomes this. Using this equation, you can also get this one. It's easy, right? And equations define the position vector for this equation. Using the right-hand rule, you can use this to get this. These two are plus, this will be minus. And substituting that in, you will get this one. Okay? You get this one. And carry it at the output. You should also write out the output and input. And one is the OD output at one side, OD input at another side. And then you just choose but you should divide it into I component first. Actually, how this come out? The first step, you should divide it in I and J components. And second one, you should know the output is in one side, okay? And it will equal to input, okay? So as long as you can see, you can also let's imagine how to calculate the acceleration without seeing the answers. It's easy. The first one, you find out the rigid body formula for here. And you use A, B, B, C, C, D to write out 3 equations. After you write out 3 equations, you will use the same formula to find out the relationship between them and combine them into 1 equations. After that, you can find out all the variable. Okay? Yes, it will be the same. First, 3 equations. Combine 3 equations into 1 equation. But now, for A, this one would be 0. Omega 1, omega 2 dot. This, RBC, omega R, omega R. They will all know. And combine them after combine them, you should rearrange them. The method for you rearranging them is, for first, you should know, you should divide it into X and Y direction. And for the second one, you should, after you have divided them, you should make them into the output is in one side and the input is at another side, right? Okay, so the lecture 12 is finished.